Many people are wrapped up in their own existence and think that humans somehow are going to rule the planet forever. But we're not. We're just like any other animal. We can be made extinct. By studying mass extinctions in the past, we begin to realize just how sensitive and precarious life is on this planet.
Throughout history, catastrophic events have devastated life on Earth over and over again. Everyone knows what happened to the dinosaurs 65 million years ago, but long before that there was an even more extreme die-off. 252 million years ago, the Permian-Triassic extinction wiped out about 90% of all marine life and 70% of all land life on the planet. Of the 5 known mass extinctions, the Permian-Triassic was by far the worst.
The question is, what caused it, how long did it last, and how long did it take for complete ecosystem restructuring and recovery?
For more than 20 years, MIT geologist Sam Bowring and his students have been searching for answers in the far reaches of China and Siberia. That's where a massive volcanic eruption began around the same time as the extinction. It was one of the most severe eruptions the planet has ever seen, lasting 1 million years and spewing enough lava to cover the entire United States in a layer almost 1 mile thick. An eruption of that scale and length would seem like a smoking gun, but the case isn't quite closed.
If you think about Earth history on a millions of years to billions of years timescale, many of the questions that come up involve the words when, how fast, over what duration. All of those things have huge implications for how the Earth was built and how it evolved over time.
If the 4.6 billion years of Earth's history were compressed into 1 year, the Earth would form on January 1st. Single-celled life would evolve around March 25th, followed by multicellular life on October 4th. Animals would show up in early November, only to be largely wiped out by the Permian-Triassic extinction sometime on December 11th. But to really understand what caused this traumatic event, Bowring and his team want to know precisely how fast it happened. That's where zircon comes in. These are more than just crystals. The precise clocks that tell time over billions of years. The key to telling time with zircon lies within its crystal structure. When zircon forms, it takes in uranium atoms. This sets the clock to 0. Here, the green candy represents uranium. Over billions of years, that uranium slowly transforms into lead, the blue candy, in a process called radioactive decay. By knowing exactly how long this decay process takes, Bowring and his team just have to measure the number of uranium and lead atoms in a sample to know how old it is. But that's easier said than done. Zircon crystals are lodged deep within volcanic rocks that the lab has to find, dig up, and ship halfway across the world to MIT.
So we take a big sample like this, that weighs a kilo or 2, and we bring it back, and we go to work on it with a sledgehammer. And once we get to that size, we put them in what we call a jaw crusher. And then we go from this stage to something that's called a disc mill, and that grinds the rock up. And from there, we take these sand-sized particles and run them over what's called a water table. And at the end, we end up with, if we're lucky, a petri dish with zircons in it.
To tell time with these crystals, the lab needs to extract just uranium and lead atoms. Nothing more, nothing less. Such a delicate job requires pristine working conditions, so they head from the dusty warehouse to the clean room, a carefully controlled environment that keeps their samples as pure as possible. There, they dissolve zircon crystals in acid and flush out everything but uranium and lead. When the samples are ready, it's time to fire up the mass spectrometer. This machine separates atoms based on how heavy they are and what electric charge they carry. First, the team loads each sample onto one of these tiny filaments. Heating up the filaments solidifies the drops, and in they go. The mass spec then separates the uranium and lead atoms and counts how many there are of each. Reading the results is like reading a stopwatch. After measuring a lot of samples over many years, Bowring's lab has made a startling discovery. Instead of taking millions of years, like the length of the eruption would suggest, the extinction only took tens of thousands of years. If we look back at the one-year calendar, that translates to about 315 seconds, a geological blink of an eye. For so much life to vanish so quickly, Bowring can't help but wonder what else could have contributed to the Great Dying.
And it could be that there's something that very fundamental about mass extinctions that we don't yet understand.
The full picture of our world 252 million years ago shows a planet in turmoil. The climate and oceans were warming, sea levels were rising, microbes were spewing methane. We see similar changes today, so there's more at stake here than just solving an ancient mystery. Take a look at the rest of our one-year calendar. One day after the extinction, the first dinosaurs evolve. After an impressive 2-week run, they get wiped out around December 26th. Humans don't even show up until December 31st. If the present day was midnight on New Year's Eve, then modern humans have only been around for about 23 minutes.
I'm beginning to see more and more relevance to the end Permian extinction and other mass extinctions to our present-day situation. This is sobering when we think about how long humans, or Homo sapiens, have been on the planet and what we have done to the planet in terms of resurfacing it, killing off all the large mammals and animals. It's rather dramatic. And so I think this short time scale for big mass extinctions is forcing people to think about what's happening today. That's not to say that we are undergoing the 6th great mass extinction, but we certainly should be worried about what we're doing to the planet.